Here is the problem. We are given four transfer functions. g1 of s equals s plus 3.5 times s plus 4 divided by s plus 3 times s plus 10. g2 of s equals s plus 8 divided by s minus 3 times s plus 200. g3 of s equals s minus 4 divided by s plus 4 times the quadratic s squared plus 3s plus 3. g4 of s equals s plus 2 divided by s plus 10 times s plus 20. Three questions. Part A. For each transfer function, determine the dominant pole and justify the choice. Part B. Which transfer function leads to undershoot in the step response? Part C. Which transfer function leads to overshoot? Notice the goal. We are not computing the full step response. We just look at where the poles and zeros sit in the S-plane and read off the answer. The whole problem is a pole-zero map exercise. Quick strategy. 5 rules let us answer all 3 parts without a single time domain calculation. Rule 1. The dominant pole is the pole with the smallest absolute real part. In other words, the pole closest to the imaginary axis. That is the slowest mode, so it dominates the long-term decay. Rule 2. If any pole sits in the right half plane, the system is unstable. That right half plane pole automatically dominates because the response grows exponentially and overwhelms every stable mode. Rule 3. A pair of complex conjugate poles with negative real part but small magnitude can dominate over a more distant real pole. Compare the real parts, not the magnitudes. Rule 4. Pole-zero cancellation. If a zero sits very close to a stable pole, that pole is suppressed and the dominant pole becomes the next slowest one. Rule 5. The over and undershoot rules. A zero in the right half plane forces the step response to dip below zero before climbing. That is undershoot. A zero in the left half plane that is closer to the imaginary axis than the dominant pole amplifies the transient and produces overshoot. 5 rules, 4 transfer functions. Now read each one in turn. g1 of s equals s plus 3.5 times s plus 4 divided by s plus 3 times s plus 10. Poles at minus 3 and minus 10. Zeros at minus 3.5 and minus 4. All in the left half plane, so the system is stable. Naive answer, the smallest absolute value pole is at minus 3. So minus 3 should be dominant, but look 1 inch to the left. The zero at minus 3.5 sits only 0.5 units away from the pole at minus 3. That is near cancellation. The two factors almost annihilate each other, and the contribution of the minus 3 mode to the step response is suppressed. The next slowest pole is at minus 10. With the minus 3 mode killed by the nearby zero, minus 10 takes over. Answer for g1. The dominant pole is at s equals minus 10. g2 of s equals s plus 8 divided by s minus 3 times s plus 200. Look at the denominator. The factor s minus 3 has a root at s equals plus 3. That is a pole in the right half plane. Right half plane pole means the system is unstable. The mode e to the plus 3t grows exponentially, while the other mode at minus 200 decays almost instantly. The unstable mode wins by a landslide. Notice the asymmetry. Minus 200 is much further from the imaginary axis than plus 3, so by the closest to Jonker rule, it is far away from dominance anyway. But even if the magnitudes were comparable, an unstable pole would still dominate because exponential growth always overtakes exponential decay. Answer for g2. The dominant pole is at s equals plus 3 and the system is unstable. g3 of s equals s minus 4 divided by s plus 4 times the quadratic s squared plus 3s plus 3. Two things to notice. First, the quadratic s squared plus 3s plus 3. Its discriminant is 9 minus 12 equal to -3. Negative discriminant means complex roots. Solving, the poles are minus 1.5 plus or minus root 3 over 2 times j, approximately minus 1.5 plus or minus 0.87 j. Compare real parts. The real pole is at minus 4. The complex pair has real part minus 1.5. Since 1.5 is smaller than 4, the complex pair sits closer to the imaginary axis. The complex pair dominates. Second, the numerator. S minus 4 is 0 at s equals plus 4, a right half-plane 0. By Rule 5, a right half-plane 0 forces undershoot in the step response. The output dips below 0 before climbing back up. Answer for G3. The dominant poles are the complex pair at minus 1.5 plus or minus 0.87 j, and G3 exhibits undershoot because of the right half-plane 0 at plus 4. G4 of S equals S plus 2 divided by S plus 10 times S plus 20. Two real poles, both stable, at minus 10 and minus 20. The closer one to the imaginary axis is minus 10, so the dominant pole is at minus 10. Now check the 0. It is at S equals minus 2. Compare absolute values. The dominant pole is at minus 10, absolute value 10. The 0 is at minus 2, absolute value 2. The 0 sits at 1/5 of the distance of the dominant pole, 5 times closer to the imaginary axis. By Rule 5, when a stable 0 sits closer to the imaginary axis than the dominant pole, it amplifies the transient and produces overshoot. The step response of G4 shoots above its final value before settling. Answer for G4. The dominant pole is at S equals minus 10, and G4 exhibits overshoot because of the slow left half-plane 0 at minus 2. Now verify by plotting the 4-step responses computed from the actual transfer functions. G1, top left, stable, monotonic, settles quickly. The minus 10 mode drives the early transient. The minus 3 mode would have lingered, but the nearby 0 at minus 3.5 cancels its contribution. Final value matches G1 of 0, equal to 14 over 30, about 0.467. G2, top right. Note the vertical scale. The response runs off to infinity as the unstable pole at plus 3 takes over. We have to truncate the plot, or the curve will leave the page. Confirms instability. G3, bottom left. The output dips below 0 in the first second. That is the undershoot caused by the right half-plane 0 at plus 4. Then it climbs and oscillates around the final value because of the complex pole pair at minus 1.5 plus or minus 0.87 j. Final value matches G3 of 0, equal to minus 4 divided by 12, about minus 0.333. G4, bottom right. Smooth rise, peak above the final value, then decay back. That is the overshoot caused by the slow 0 at minus 2. Final value G4 of 0 equals 2 divided by 200, equal to 0.01. 4 transfer functions, 4 signatures, 4 step responses. Summary. Dominant poles. G1 minus 10 after the nearby 0 suppresses the minus 3 pole. G2 plus 3, the unstable pole. G3, complex pair at minus 1.5 plus or minus 0.87 j. G4, -10, with the -20 pole twice as far away. Undershoot, only G3 because of its right half-plane 0 at +4. Overshoot, only G4 because the 0 at -2 sits 5 times closer to the imaginary axis than its dominant pole. The big picture. The S-plane geometry tells you everything. The pole closest to the imaginary axis dominates the decay rate. A right half-plane pole wrecks stability. A right half-plane 0 forces a dip below 0. A slow left half-plane 0 amplifies the transient. And a 0 near a pole cancels it, shifting dominance to the next pole over. 5 rules, infinite systems, no simulator required.